All right. So we're going to pick up talking about, kind of how rectangular and polar coordinates go together. Considering the polar and rectangular coordinates together, the polar axis coincides with the positive x-axis and the pole coincides with the origin. A point P not on the origin has a rectangular coordinate xy and a polar coordinate r theta, and they both represent the same point. Well, there's a relationship in between our rectangular and polar coordinates. And we're going to use SOHCAHTOA to develop that relationship. So if you take a look at this diagram that we have right here, this point that's represented by the ordered pair r theta and xy. Well, we're going to think about xy because that's what we're more comfortable with. So to get the point xy, you'll see we want a distance of x on the x-axis and then a distance of y vertically, and we've created this right triangle. So using our SOHCAHTOA rules, we know that sine of theta is equal to opposite over hypotenuse. And if I solve this equation for y, I get y is equal to r times sine of theta. Well, that brings us to one of our rules for converting between rectangular and polar coordinates. We can do the same thing with cosine. So if I cosine of theta, that's going to be x over r, and we can solve this for x and get that x is equal to r times cosine of theta. Tangent, we know that tangent of theta is equal to y over x, and that is the equation we have listed here. And then the fourth equation is simply Pythagorean theorem, x squared plus y squared equals r squared. So these are all things that we already know, relationships that we already know about right triangles. It's just SOHCAHTOA and Pythagorean theorem. We're going to use these relationships to convert back and forth between rectangular and polar coordinates. The first two we typically use to convert from polar to rectangular, and the second two we typically use to convert from rectangular back to polar. So we want to determine the rectangular coordinates of each point in polar coordinates. So we're converting from polar to rectangular. You know that you're in rectangular when your variables are only x and y and you don't have any r's or thetas. So here's our r, here's our theta. Don't make this hard. X is equal to r times cosine of theta. Y is equal to r times sine of theta. And then we just need to clean this up. Cosine of 30 degrees, square root of 3 over 2. So we end up with 3 square root of 3. And then sine of 30 degrees, that's a half. So we get 3. Our ordered pair in rectangular coordinates, 3 square root of 3, comma 3. Questions at all? All right, let's try another one then. Here we have that our r value is -4 and our theta value is 7 pi over 4. X is going to be r times cosine of theta. And y is going to be r times sine of theta. cosine of 7 pi over 4, that's square root of 2 over 2. And then sine of 7 pi over 4, that is negative square root of 2 over 2. So x is a negative 2 square root of 2. Y is a positive 2 square root of 2. We get the ordered pair. Negative 2 square root of 2, comma, 2 square root of 2. Questions, anybody? All right, now let's go the other direction. This time I've given it to you in rectangular coordinates, and I want you to come up with the polar coordinates. They've given us x and y. Well, r squared is equal to x squared plus y squared, so we'll start by finding r. We could even say that, r is going to be the square root of 2 squared plus negative 2 squared. So that's going to be the square root of 8. Two square root of 2. And then to find our theta value, we're using the fact that tangent of theta is equal to y over x. So tangent of theta is going to have to be negative 2 over 2. Tangent is negative 1. So theta is going to have to be tan inverse of negative 1. Well, we know that our calculator is only going to spit out an answer between negative pi over 2 and pi over 2. But we also know that there's always that sister triangle, that sister answer, if we're looking at the whole unit circle. So what we need to do is we need to figure out which of the two answers, because tangent is negative 1 at the 45-degree reference angle in both the second and the fourth quadrant. And we need to figure out which one of those angles we want to use. The way that we're going to determine which angle to use is actually by going back and looking at this original ordered pair. If we were to plot this point to negative 2, we see that we're in the fourth quadrant. So when we come up with our theta, we need to make sure that our theta is in the fourth quadrant. We actually have two different options here to get us in the fourth quadrant. We could say negative pi over 4 or 7 pi over 4. Since those are coterminal angles, and we've discussed that there are an infinite number of pairs of polar coordinates that represent a particular point. So you could choose whichever one you like. Usually I pick the one that's positive, but it doesn't make a difference. Our final answer is the ordered pair 2 square root of 2, 7 pi over 4. All right, let's try another one. Any questions on this one? I'm sorry, before we move on to the next one? Okay, our R value is going to be the square root of x squared plus y squared. So R is going to be the square root of 1 plus 3. We get R to be 2. And then we want to figure out our angle. Tangent of theta is going to be negative square root of 3 over negative 1. So that's tangent of theta equals square root of 3. theta is going to be tan inverse of square root of 3. So we need to find our angle here. Tangent is square root of 3 when we have square root of 3 over 2 on top and 1/2 on the bottom. So that means y has to be square root of 3 over 2 and x has to be 1/2. And our tangent value is positive. Tangent is positive in quadrants 1 and 3. But which of those two quadrants do we actually want to be in?
The third, because our ordered pair are both negative.
Exactly. We want to be in the third quadrant because our ordered pair x and y are both negative. So I need to come up with this angle in the third quadrant. X is the short one. Y is the long one. So that's got to be a 60-degree reference angle there in quadrant 3. So that makes theta 4 pi over 3. We get the ordered pair in polar coordinates 2 comma 4 pi over 3. Questions, anybody? I think the trickiest part with this is just remembering to verify which quadrant you're supposed to be in based on the rectangular point. The graphs we've studied in algebra and trig so far have used rectangular coordinates. An equation where x and y are the variables is called a rectangular equation, but an equation where r and theta are the variables is called a polar equation. So polar equations can look a couple different ways. R equals 3 sine theta, R equals 2 plus cosine of theta, R equals theta. We could have just, yeah, R equals 5. There's a variety of different ways, but basically X and Y are not your variables. R and theta are your variables. So we're going to practice going back and forth between rectangular coordinates and polar coordinates for equations. And we're still using the same rules. We're using the fact that X is equal to R times cosine of theta and Y equals R times sine of theta. We're going from rectangular to polar, so that means get rid of the x's and y's and introduce r's and thetas. So I'm going to get rid of the x by replacing x with r cosine theta. And then I'm going to get rid of the y by replacing y with r sine of theta. And now we've gone from rectangular coordinates to polar coordinates. But we don't want to leave it quite like this. Just like with rectangular coordinates, we usually like it y equals whatever. With polar coordinates, we like our equations to be r equals whatever. So we do want to solve this equation for r. Notice that we have a linear r showing up in both of our terms. We are going to factor an r out. And then we can divide both sides by what we have in the brackets there and get that r is equal to 8 over cosine of theta plus 5 sine of theta. And that is our polar equation. Questions? All right, let's try another one. Let's transform x squared equals 6y from rectangular to polar. We're going to replace x with r cosine theta. So now it's going to be this whole thing squared is going to be equal to 6, and then we're going to replace the y with r sine of theta. That outer exponent of 2 is going to get applied to both the r and the cosine, since our operation in between the two is multiplication. So we're looking at r squared cosine squared equals 6r sine of theta. The variable that we're solving for is r, so if I take a look at the r's in our equation, I got an r squared and an r to the first. That means that this is quadratic in form. To solve any quadratic equation, we like to set it equal to 0, and then we can either try to factor it or use quadratic formula if we absolutely have to. So I want to get all of the terms on one side of our equation so we can, solve it one of those two ways. Well, I'm going to try to factor it before I feel like I have to do something with a quadratic formula. So I'm going to factor an r out. It's going to leave us with r cosine squared minus 6 sine. And then I can use my zero product property and set each factor equal to 0. We get r equal to 0, and then r cosine squared minus 6 sine equal to 0. Well, this one's already solved for r. Let's solve the other one for r. We'll add 6 sine to both sides. And then divide by cosine squared. I get r equals 6 sine of theta over cosine squared. Any questions so far? Well, you'll notice in this example that we got like two answers. We got r equals 0 and r equals 6 sine over cosine squared. Well, we don't really want two equations. What we need to do next is determine whether r equals 0 lives inside r equals 6 sine over cosine squared. The way that we're going to do that is, if r equals 0 and r equals 6 sine over cosine squared, that means that 0 has to be equal to 6 sine over cosine squared by our transitive property of equality. Well, how do I show that r equals 0 is included? If, when I set it equal to 0, I can obtain a solution. I don't even care what the solution is. As long as I don't get no solution, that tells me that r equals 0 lives inside that other equation. So I'm going to cross multiply here. Zero times cosine is 0. 1 times 6 sine is 6 sine. And we're solving for theta. We'll divide by 6. And then we'll inverse sine. We get theta equals inverse sine of 0. Do we get an answer? Does sine have a value of 0 somewhere? Sure it does, right? At pi and at 0. Since we got a solution, r equals 0 is included in r equals 6 sine over cosine squared. So our only answer is going to be r equals 6 sine over cosine squared. Questions? Let's try a couple more then. Let's transform the equation r equals 4 sine theta from polar to rectangular. So now we're going the opposite direction. So we're going to be using our other two equations. We're going to be using the fact that r squared equals x squared plus y squared, and we're going to be using the fact that tangent of theta is equal to y over x. Well, I'm not seeing anything too promising, so I think I'm going to write the rest of them down to see if that helps inspire me. All right, well, I have r and I have sine. In order for me to substitute here, I have to have like a r sine, and I have just sine. How could I get an r sine? Any ideas on how we could secure an r on that right-hand side so we could substitute y in for r sine theta?
Divide it over.
Well, if we divide it over, is it going to be up in the numerator multiplying itself by sine?
No.
No, so that's a good idea, but not quite it.
Can you multiply by r on both sides?
Is that a legal math move for us to multiply both sides of an equation by the same thing?
Yes.
Sure is. So that's exactly what we want to do. And when we do that, we're going to get r squared equals 4r sine of theta. Well, we know that r squared is equal to x squared plus y squared, and we know that r sine of theta is equal to y. So I can replace that with y to be in rectangular coordinates. It means that our variables are all x and y and no r's and thetas. We've gotten rid of r and theta. Right there is our rectangular form. Can anybody tell me what the graph of that looks like? Going back to our algebra knowledge.
A parabola.
Not quite. It would be a parabola if x was squared but not y. And here they're both squared.
Oh, a circle.
Yeah, this is going to be a circle because x and y are both squared. Questions, anybody? All right. Let's try another one. This time we're going to transform the equation theta equals pi over 3 from polar coordinates to rectangular coordinates. So basically, I got to get rid of that theta. Look at all my options over here. Well, I don't really want to introduce an r, right? Because then I'm going to have two problems. I'd like to just deal with the one problem of theta. We have the equation that says tangent of theta is equal to y over x. We have that theta equals pi over 3. Well, we can solve this equation for theta, can't we? Theta is equal to tan inverse of y over x. So I can substitute tan inverse of y over x in for theta, again, using this transitive property of equality. So we get that tangent of theta, tan inverse of y over x is equal to pi over 3. And then using our definition of tan inverse, we get that y over x is equal to tangent of pi over 3. Tangent of pi over 3 is just a value on our unit circle. Tangent of pi over 3, that's square root of 3 over 2 over a half, square root of 3. We've eliminated theta. We haven't introduced r. We're left with x and y. There's our polar. But we typically like to solve it for y when it's linear. We get y equals the square root of 3 times x. That's really better. What's the graph of that one going to look like?
A line.
Yeah, that's just a line, right? Y to the first, x to the first. This is just linear. It happens to be a slope of square root of 3, which happens. Questions, anybody, before we go to our last one? All right, let's transform the equation r equals 4 from polar coordinates to rectangular coordinates. So we want to get rid of the r, not necessarily introduce a theta if we don't have to, and be left in our final answer of x and y. Our only equations that have an r squared equals x squared plus y squared. X equals r cosine theta, and y equals r sine theta. As I mentioned, I would prefer not to introduce a theta if I didn't have to. So if somehow I could just deal with the other equation with r squared, then that would be better. Is there any way that we can legally turn that r into an r squared, and then all we'd have to do is substitute x squared plus y squared in for r squared?
Multiply r on both sides again.
So let's try that. If we multiply r on both sides again, I get r squared on the left, but on the right, I'm going to get 4r. So I can substitute in for this one, but now I've created another problem over here. So is there maybe something else we could do? That was a good idea. It worked before, right? Now why not try it again? What's another way other than multiplying both sides by r to transform an r into an r squared?
Did we square both sides?
So is that a legal math move? If we square one side, can we square the other side of an equation? Sure, whatever we do to one side, we do to the other. What's not a legal math move that I tell you guys not to do is you can't square the top and the bottom of a fraction. But if it's an equation, as long as we do it to one side, we can do it to the other side. So this turns into r squared equals 16, and now we can substitute x squared plus y squared in for r squared. We get x squared plus y squared equals 16. To circle again, centered at the origin, radius of 4. Questions on plotting points in polar, converting points and equations between rectangular and polar coordinates. Questions at all on that? In the next section, we're going to be graphing polar equations. Before we start graphing these equations, we want to talk about symmetry. Now, we talked about symmetry with respect to the x-axis, y-axis, and origin in college algebra. This is similar but different. It's still that same idea. We're going to have 3 different types of symmetry, but this is symmetry I actually use. We practice testing for symmetry in college algebra, but honestly, I never do that before I graph something. I'll just graph it. But with polar, you want to know the symmetry because graphing polar is a major pain in the butt. So if you can know that you have the mirror image left and right or up and down, it makes your workload a lot less. So we're going to be looking at 3 different types of symmetry. Symmetry with respect to the polar axis, the line theta equals pi over 2, and then the pole. So these are basically the x-axis, the y-axis, and the origin in polar coordinates. So here we have a picture of a graph that is symmetric with respect to the polar axis, which coincides with the x-axis. So we're, mirror image above and below. If the point r theta is on the graph, then the point r negative theta is also on the graph. Remember, with polar, we go to the angle first, and then we go out r units. Oh, you'll notice that r units takes us at the same distance, but theta puts us either above or below our polar axis. So the test is to replace theta with negative theta, and then you're going to clean it up. If the equation remains unchanged, that is, you get the original back, then the graph of the equation is symmetric with respect to the polar axis. When you do the cleanup for this, when you're replacing theta with negative theta, you need to remember your negative angle identities for sine and cosine, because most of the time our polar equations have sine and cosine in it. So remember that cosine of negative theta is equal to cosine of theta, and sine of negative theta is equal to negative sine of theta. We're going to be using that a lot with the symmetry. The next type of symmetry is symmetry with respect to the line theta equals pi over 2. This is the same as symmetry with respect to the y-axis, because the line theta equals pi over 2 coincides with our y-axis. This, it's a little bit trickier, right? If the point r theta is on the graph, then the point negative r negative theta is also on the graph. Well, negative theta gets us down here, but that's not where we want to be. In order to have symmetry with respect to the line theta equals pi over 2, we're looking left and right. So in order to get me in the opposite direction into the second quadrant, I make r negative. Because remember, if our r value is negative, then when we plot our point, we go in the direction opposite of our angle. So that's why both of them are changed here. Our test is to replace r with negative r and theta with negative theta, and then clean it up. If we get the original back, then the graph displays symmetry with respect to the line theta equals pi over 2. And here again, we'd be using our negative angle identities. Anytime you're replacing theta with negative theta, you're going to be using your negative angle identities. And then last but not least is symmetry with respect to the pole, which coincides with the origin. Here, if the point r theta is on the graph, then the point negative r theta is on the graph. Remember that symmetry with respect to the origin is like diagonal symmetry. That's how I always think about it. And for us to go diagonally in the opposite direction, we just make the r value negative. So we're replacing r with negative r. If the equation remains unchanged, that is, we get the original back, then the graph of the equation is symmetric with respect to the pole. So here's one thing that's really different for symmetry with polar equations. If a polar equation passes a symmetry test, then we know its graph has that symmetry for sure. But if a polar equation fails a symmetry test, we can't say it doesn't have that symmetry for sure. It's a maybe. It may or may not have symmetry, but you can never say absolutely no, it does not have that type of symmetry. So when you're answering these, it should either be yes or maybe. No no's. So we're going to do a few graphs. We are going to test them for symmetry, make an r theta chart, like an xy chart, but r theta chart, and then plot our points. So I've put these kind of in classifications of graphs. Any graph that's of the form, any equation that's of the form r equals a cosine theta or r equals a sine of theta, that graph is going to produce a circle. Honestly, I don't remember that stuff. I don't know. I feel like once I get the points, I can kind of just figure out what shape it's going to be. So that's not something that I personally choose to memorize. So let's graph r equals 4 sine of theta. First, we want to test for symmetry. And I'm going to make the same kind of chart that I make when I am in college algebra. Polar axis, theta equals pi over 2, and the pole. I'm going to do 3 tests. For polar axis, I replace theta with negative theta. For r equals pi over, for theta equals pi over 2, I replace both. And then for the pole, I just replace r. So be careful, especially those of you who are doubling up with college algebra right now, because when we make this table for college algebra, it's, replace y with negative y, x with negative x, and then both. So here, the both is in the middle, so just be careful and don't confuse the two. All right, let's test for symmetry. I'm replacing theta with negative theta, so we get r equals 4 sine of negative theta. We're going to clean it up using our negative angle identity. We end up with negative 4 sine of theta. Is that our original? Nope. But I can't say no to the symmetry. I just have to say maybe to the symmetry, because it may or may not display that symmetry. The algebra doesn't tell us for sure. Kind of like with intermediate value theorem, right? We could get a for sure yes, otherwise it was inconclusive. Same kind of thing happening. We can get a for sure yes, but not a for sure no. For symmetry with respect to the line theta equals pi over 2, we're replacing both. We'll start with our negative angle identity. We know that sine of negative theta turns into negative sine of theta. I look to see if it's my original. It's not, but what could we do?
Divide by -1.
You got it. Same trick that we did in algebra. And divide both sides by -1. We're going to get r equals 4 sine of theta, which is our original. So this is a for sure yes. Symmetry with respect to the line. Theta equals pi over 2. And then the last type of symmetry that we are checking for is symmetry with respect to the pole. This is where we're going to replace r with negative r. There's no negative angle identity to apply. I'm going to try to get rid of that negative. Really, the only way I can do that is by dividing. And that just moves the negative to the other side. Still not the original. So this is a maybe on its symmetry. Questions on the symmetry?
So when we answer those, we answer it in like 3 parts like that?
Mm-hmm.
Okay.
Because we're doing 3 different tests. Now it's possible. I imagine on my math lab when I pull it up, it's going to be like a 4-part question. Is there symmetry with respect to the polar axis? Is there symmetry with respect to theta equals pi over 2? Is there symmetry with respect to the pole? And then graph. All right, so what we have to do to make this R theta chart so that we can graph this is we have to go all the way around the unit circle. You have to choose every single theta value from the whole unit circle, 0 all the way around to 2 pi. Crazy. So the symmetry thing is so helpful. Since we have symmetry with respect to the line theta equals pi over 2, so that's this right here. We have symmetry with respect to this line. That means that if we get quadrant 1 and 4, we can just flip it over and get quadrant 2 and 3. Or if I get quadrant 2 and 3, I can just reflect it over the line and get quadrant 1 and 2. This is great because it is now cut the size of our R theta chart in half. Because instead of having to do every point on the whole unit circle, I only need to do 2 quadrants. So I got it started, and I already made the R theta chart for us. I chose the first and the 4th quadrant. So down here are my theta values for the first quadrant. 0 to pi over 2. There's quadrant 1. And then over here, from 3 pi over 2 to 11 pi over 6, there's my quadrant 4. And then we're just taking all of those values and plugging it into R equals 4 sine of theta for our theta value. And I already got the corresponding values for us. Now it's time to plot those 9 points. And then we will reflect it about the line theta equals pi over 2 to get the rest of the points, and then we will connect our dots. So let's start with 0, 0. So I go to angle 0, and then I go out 0 units, 0 rings. So my first point's right on the pole. Now we go to our next angle, which is pi over 6. Now careful, notice this graph paper goes by 15. See how there's so many lines? So make sure you're getting all the way to pi over 6, which is right here. And now we're going to go out 2 rings, because that's our R value. 2 is positive, so we're going in the same direction as the angle. Next up is pi over 4. We're going to go to the angle first, and then go out R rings, 2.8. That's right about there. Our next angle is pi over 3. So here's pi over 3, and now we want to go 3.4 rings out. And then at pi over 2, tells us to go 4 rings. right there. Questions on plotting any of those 5 points? All right, well, let's do the other 4 points then. So we're starting at our angle of 3 pi over 2. Notice that our R value is -4. Since our R value is negative, we're actually going to go in the direction opposite of our angle, and I'm going to go 4 in the opposite direction. 1, 2, 3, 4. Well, that ends up being like right on top of this one here. Next up is our angle of 5 pi over 3. There's our angle right there. Our R value again is negative, so we're going to go in the direction opposite of our angle, and we're going to go 3.4. Right here. Our next angle is 7 pi over 4. Again, we have a negative R value, so we're going to go 2.8 rings in the opposite direction. And then last but not least, 11 pi over 6. There's our angle. Our R value is negative, so we're going to go in the direction opposite of our angle, and we're going out 2 rings. Right there. So those are the points that I get from the 4th quadrant angles. Any questions on plotting those points? All right, well, now it's time to get additional points using symmetry. We know that our graph should have symmetry with respect to the line theta equals pi over 2, which is right here. So if you look at all the points that you have, do they match on the left and the right-hand side? Yeah. Yeah, they already do. So I actually don't need to get any additional points by reflecting. Don't worry, we'll have some examples where we do. So this is it. I'm ready to just draw in my graph, and I like to start and do increasing theta. So there we go. And it looks a lot like a circle. Questions, anybody? All right, let's try another one. These next ones, see, a circle, it was just like a cosine and sine with a coefficient, and that was it. And that's how you knew that it was a circle. Lima cones, it could be, it's going to have a coefficient on sine or cosine, and it's going to have plus some number. And you'll see where it says that A and B are both positive. So whatever we're adding has to be a positive number for it to be this. So we want to start by testing for symmetry, and we'll do our 3 types of symmetry. Symmetry with respect to the polar axis. where we're replacing theta with negative theta. Symmetry with respect to the line theta equals pi over 2. This is where we're replacing r and theta with the opposite. And then lastly, symmetry with respect to the pole, and here we're just replacing r with negative r. I'm going to pause the video and put you guys into groups and let you work on this symmetry. Okay, so our symmetry should have gave us yes, maybe, maybe. Some people had maybe for that first group, but remember, we're using our negative angle identity, and cosine of negative theta is equal to cosine of theta. So we're just replacing cosine of negative theta with cosine of theta, so that one's definitely a yes. That's why when I did my r theta chart, I only chose theta from 0 to pi, because if we have symmetry with respect to this polar axis, then we're only going to have symmetry. All we need to do is get points in either quadrant 1 and 2 and then flip down, or get points from quadrants 3 and 4 and then flip up. So I chose quadrants 1 and 2 and got those points. So I'm going to graph them. Apparently you guys all have already, so I got to catch up. So going to angle 0 and then out 3, angle pi over 6, 2.73. All right, so then here I'm out at 3 pi over 4, but my r value is negative, so I need to go backwards. Again, with 5 pi over 6, I have a negative r value, so I'm going to be going backwards. And then at pi, negative r value, so I'm going back here. All right, so those are my points, but we have symmetry with respect to our polar axis, and we can see now that clearly it does not match above and below our polar axis. So we need to reflect each one of these points about this line to obtain additional points. So I'm just gonna start here and kind of work my way from left to right. So this one's gonna flip down and be here. This one flips up to be right here. And right here. Now I'm gonna flip these points down. That's right at 2. And we get these points. Any question on getting the points based off of the symmetry? All right, so now we want to draw it in, and we want to, again, kind of draw it in increasing theta. So I'm going to start here at 0. And then just keep going. And I know it should match on the top and the bottom. So it's like a circle with a little loop-de-loop in it. Questions, anybody?
So, like on a test, are you going to give us the coordinates like you have it set up here?
No. No, I'm not. Sure, it's going to be multiple choice, like pick a graph.
Oh, okay.
Anybody else? Questions? All right. Let's see. I'm just picking which one I want to do. I think I want to do the rose one. Since we only have time for one more, let's do this one. So a rose curve in polar coordinates, you don't have a plus or minus a constant. What happens? What our equation is going to be a times sine or cosine, but you're going to have some number multiplying inside the argument. These are rose curves. If n is even, then the number of rows, then the rose has 2 n petals, but if n is odd, then the rose has n petals. Again, I don't really like memorize this kind of stuff because I feel like that I'm going to see what the graph looks like when I draw it out. But let's test for symmetry. Oh, polar axis. Theta equals pi over 2, and then our pole. So for our polar axis, we're replacing theta with negative theta. But we know with cosine, that negative kind of just disappears with our negative angle identity. We've gotten our original back, so this is a yes for sure. Testing symmetry with respect to the line theta equals pi over 2, we're replacing both. Cosine of 2 theta, cosine of negative 2 theta turns into just cosine of 2 theta. And then I can try to get rid of that negative on the left by dividing everything by a -1, but still doesn't get us back to the original. So this is a maybe. And lastly, symmetry with respect to the pole. We're replacing just r with -r. And this does not turn back into the original, even if I divide by -1, so we got another maybe. Only symmetry with respect to the polar axis. So that's this one. That means I need angles out of quadrant 1 and 2. So I'm going to run from 0 to pi. And we just plug those values into our calculator, making sure we're in radian mode. And let's plot our points. First up, we're at 0, 3. Then pi over 6, 2. Pi over 4, 1. Pi over 3, 0. At pi over 2, our r value is negative, so we're going in the opposite direction. Three pi over 2, we're back at 0. 3 pi over 4, we're out at 1. 5 pi over 6, we're at 2. And pi, we are at 3. Questions on plotting the points? I know I went kind of fast, but you guys seemed like you were good at plotting the points before, so I just rolled through. Anybody have any questions or need me to pause for a minute?
When you did the first part, theta equals pi over 2, where did that angle measure come from?
Theta equals pi over 2. Okay, say that part again.
Like in the first part when we did the 3 tests.
Right
did-
here.
Yeah, where did theta equals pi over 2? Is that just what we always go
That's
to?
always what it is. That represents the y-axis
Okay.
because where is pi over 2? Right here,
Okay.
right? So that coincides with the y-axis. So that's just the y-axis in polar coordinates is theta equals
Okay.
pi over 2. Anybody else? Our graph has symmetry with respect to the polar axis. Right now, we definitely do not have the mirror image, top and bottom. So we're going to create the mirror image by reflecting points. So this one reflects down here. This one is here. This one comes up. This one comes down. This one comes down. All right, now my points match. And then I am going to draw it in increasing theta. So we started out here at 0, 3. Well, I guess technically that's 3, 0. And then I'm going to connect. And I came down, back up. And now I just need to make it symmetric to that. Now that I have that part, I just know the other part matches. So I'm going to draw it in. I think these ones look extra cool. So there we go. That's a rose curve. And they just call it a rose curve because it has like these petals. And you'll notice that our n value was 2, so it's even. So it says if your n value is even, you're going to have 2 times n petals. 2 times 2 is 4. We got our 4 petals. And that is the end of trigonometry, you guys. We are stopping there this semester. So congratulations on making it to the end. Does anybody have any questions about anything before we part?
Would it be possible for you to post Tuesday's lecture?
Yeah, I know, I forgot. Yeah,
Okay. Thank you.
my kid ended up doing something bad and got in like super trouble, and then that kind of just changed the course of the day. Then I forgot. So yeah, I'll get that up right away.
Will you also get today's lecture up as well?
I sure will. I sure will.
Do you have a answer key to that?
I do not have an answer key to that. That was all on the agenda this semester to get done, and then it didn't because remote instruction.
Yeah, I could find it very helpful to have an answer key.
Yes, I bet you would. So what I would encourage you all to do is, I mean, you're working on it. Why don't you start posting your answers on the discussion boards in D2L, and then you guys can be cross-checking with each other, and then I will be very grateful because you guys would be developing an answer key for me that I could then use and make a nice answer key for your peers in the future. My pre-calc class wants an answer key too. I made them a review, 97 questions, no answer key.
Will this last part, the lemniscates, will that be on the exam?
I mean, maybe, yeah, but it's just the same thing. You're just
Okay.
testing for symmetry, and then you're plotting the points. It's no different.
Okay.
I mean,
Is it
there's like
like a-
15 different kinds of polar equations. I just chose a couple.
Would you say like the test is an even mix of everything, or like has a little more?
I haven't made it yet, so I
Okay.
wouldn't say it's going to be an even mix of everything because that first stuff is like so easy now. You know, what's the reference angle? Like, Probably not. We were talking a little bit in the review session. I pulled out my paper final. My paper final that I usually give, I was a little surprised. It was only 20 questions. So I guess because it's open book, it'll be a few more questions than that. Because of course I had like a non-calculator part and a calculator part. But I think that's about right. 25 questions or so. I'm going to hit the big things, the things that are important. Your ability to, solve equations, your ability to graph.
And you will be giving partial credit for everything we do if we submit our answers.
Nice legible work. There's going to be this new stuff. There's going to be parametric equation stuff. There's going to be polar equation stuff. There's going to be applications of vectors. You're going to have to solve triangles. There's going to be a decent number of application problems on it, because that's kind of what we do with trig, is we apply it to things. Don't forget all the angular speed, linear speed, arc length, area of a sector applications that we did in, maybe that was chapter 3. Chapter 2 or chapter 3. Definitely going to have to graph trig functions. So it's going to be like the bigger concepts and less of the smaller concepts, because we use all those smaller concepts inside the bigger concepts. Although I might pull some of like the vocab questions. But again, to me, a final exam is, do you know the most important stuff at the end of the semester? Yeah, I'm probably going to put a couple more questions on than I normally would, just because it's open book now. But, it's not a fine detail type test. It's a bigger picture test. Anybody else? Anything?
So it's just really the most important stuff to know.
Yep. Things that I've harped on, things that we've used over and over and over again. But
And
like
not
I
like
said,
that one case that is in in one chapter in like the back of the book or something that's like
what?
hiding.
What?
It's not going to be like this like one formula that's hiding somewhere. That's like the thing.
I think I'm usually pretty fair, guys. I think I'm usually pretty fair. But it is open book, so to be fair, I could just have it be at the back of that page, but I probably won't. Yeah, I'd count on like 25 questions. All right, if you have not taken that survey, be sure you do that. Like, I'm having to assign 150 students in specific time slots on specific tests and stuff, and it's kind of complicated on my end. So please get the survey done so I can have some time to do this. I am not working on Mother's Day, so I need to get it all done by Saturday. If you guys have any questions, please feel free to email me. Like I said, I will not be responding on Sunday, but other than that, I can be available any day. Good luck, everybody. Let me know if you have any questions.